Unit 2 is on differentiation, where we go away from the definition and we learn a bunch of shortcuts. And if we looked at these examples, the x squared one we did already using the definition, and we got the derivative to be 2x. We did some variations with x cubed. If you did the derivative, you would get 3x squared. But if you thought about the definition of the derivative, and you had to do x to the 4, or this 4x to the minus 3, all of a sudden it would be like, oh, that's going to be tedious. And we're going to get to a place where we can say, we can just look at these ones and say, these are the following answers for the derivatives of each of these. And so sometimes what happens in mathematics is after you've done something the long way for a long time, you start to notice patterns in the results. So all of these ones with powers have a pattern that's happening. Take a moment to look at them and see if you can see what's happening in the pattern. How could I go from this with a 7? What do you think the answer is going to be? 7x raised to the power 6. Good. So we've seen some of the things happen. What's happening?
Moving the current exponent to move it as a constant and then subtracting 1.
So the 7 is like it's coming out in front as a coefficient, and we're subtracting 1 from the exponent. Did that work with this one with the 3 out in front?
Yes.
Yeah, because when that 3 came out in front, it multiplies by that other 3 and became a 9. So does it work with other more complicated ones? What could I do with the square root of x? Could I make that into an exponent? Does it work? Yes, it does. Could I write 5 as x with an exponent? It's the same as 5x to the 0. What would happen if that 0 came in front?
0.
And the derivative is 0.
Because it has no slope.
And this one? If you did the same thing, can you see that you would get 7x to the 0? But what will we write instead of that? We'll just write 7. This would be x to the 1/3. Bring that 1/3 out in front, subtract 1 from the exponent. How are you going to work with this one? This is 1 over x to the half. How could I move that x to the half up to the top? X to the negative a half. And so the negative a half comes out in front. Subtract 1 from a negative a half. We get negative 3/2. So we have a couple of rules come up. The constant rule. If it's a constant, you will always get 0 when you do the derivative. And then the power rule, anytime you have a power, when you do the derivative, that power can come out in front and subtract 1 from the exponent. Yes?
What is that upside down A?
Okay, so here are some new notations just for fun. The upside down A is shorthand for all. And you won't have to write that, but I just thought I would show it to you. Sometimes when you're doing a lot of advanced math and you're getting tired of writing for all, a lot of times you make a symbol up for it. And really, it's only 6 letters. How annoying should it be to write it? But mathematicians want to make things as short as possible. So instead of saying for all real numbers, you can just write this, symbols instead.
So wouldn't that be if you read it for all n elements of the real?
for all real n, for all elements of, for all n that belong to the real numbers.
So those are whole numbers?
That'll include whole numbers, but it includes fractions, it includes decimals, it includes all real numbers.
Okay, so I think it's not.
So it doesn't have to just be whole numbers. It works with all real numbers. Yeah. My favorite one in university was this shorthand. I like that one.
If and only if.
If and only if. If.
Yeah, I don't like that. You make that one line.
And if you have a number in front and you do the derivative, that number in front doesn't affect the rule. So what that means is when we have 8x to the 5, you can do the derivative of x to the 5 just like before, where the 5 comes out in front and subtract 1 from the exponent, and that 8 in the front just would stay there. Well, this makes our life a lot faster than the definition. I probably shouldn't have shown you this lesson before tomorrow's quiz. But, oh well. Because tomorrow's quiz, you're going to have to use the definition of the derivative. You're going to look at the question, instantaneously know the answer, and then spend 5 minutes trying to get it. My apologies.
I think it's good to enjoy this thing. I'll let you about it.
So we start off with the derivative. This is an easy one. You ready for the answer? You got it? Did you get negative 15x to the 4? Yes.
Would it have been alright to write y prime? Or?
Well, in this one, since it was written find dy dx, then that's why the answer is written with dy dx. And again, what I'm trying to do in these examples in your notes is I tried to find all the different terminology and ways that different textbooks have asked the same question. So here's find dy dx. This next one, differentiate. Okay? So it's same as differentiate with respect to x is same as like find y prime. So you can write y prime equals. Well, before we do that, this one is a medium one because the initial way that it's written isn't written in a way that we could use our power rule. We have to take our original equation and rearrange it a bit. Can you see that I could write it like that? That I would need to move that x to the 8 from my denominator into my numerator. And I can do that with my negative exponent rules. And now I can find the derivative. That negative 8 can come out in front. Negative 8 times 3/4, negative 6. This is where you're going to make a mistake. You want to subtract 1 from the exponent, and you're going to be tempted to write 7. Because 8 minus 1 is 7. But you have a negative 8. Subtract 1 will get you to a negative 9. So that's a medium one. Here's another way of finding the derivative. This is another easy one, but it says find d dx, and then they have something in brackets. That d dx is like an operator or a function. It's derivatizing what's inside. That's not a word. Okay? But it says find the derivative of what's inside. And if we would do that, dy dx would be 28x cubed. Now, if I wanted to be really focused on notation, and I will not deduct for this, but if I was really focused on notation, I would get mad at myself here a little bit because I introduced a y and there was no y given. So if I wanted to write this properly, I should do this. That would be more proper. Or I should have defined y, and then I would be fine. So that's just proper terminology. So when we're dealing with things, we don't want to introduce variables that aren't there. And so this would be more proper. So there was, when I first wrote dy dx, there's no y anywhere. So it doesn't really mean anything when I write dy dx, unless I define y somewhere else, and then it would have been fine. And so in this case, this would be a better way of writing it notation-wise. And this is about as hard as these ones get. When you get to your radicals, how do we change radicals to exponents? So I'll start the cube root means to the 1/3. Eventually, and probably for many of you now already, you probably could have made that x to the 2/3 right away. Okay, but the whole thing to the power of 1/3, and now that x to the 2/3 is in my denominator, so it becomes x to the negative 2/3 if I wanted to move it to my numerator. Now I can find my derivative. My numerator, my exponent comes out in front, so that'll be negative 14/9. Subtract 1 from the exponent, and one of the things that differentiation gets you really good at is subtracting 1. Very important skill. But you're going to have to subtract 1 with all sorts of fractions. So if you have negative 2/3 and you subtract 1, that'd be like subtracting 3/3. And we get negative 5/3. So for the power rule, this is about as difficult as they get. Working with radicals, working with your exponent rules and fractions, and solving them from there. So if you had the answer, what would this have been originally? X to the 5. And we're going to find out later that this isn't the only answer to this one. But for now,
Wait, because you could go further down or further up.
for now, this is one of the answers. Okay? Similarly, if you had to work backwards in this one,
4x to the 3.
and you can always check by applying the derivative. And again, later we're going to find that another possible answer would be having a plus 7 here. Or if you have a, does anyone have a favorite number that they feel has been underrepresented in their math courses?
13.
15? So teacher never uses 15 in their questions. You could say plus 15. This would be another possibility. Because what's the derivative of just a number? 0. And so there could be anything there. And that's what, when we get to that, and that's 2 units down the line, we will eventually have, the answer to this is 4x cubed plus c, and then we could define c as any real number.
So if
But,
so if it's 4x cubed plus infinity or negative infinity,
well,
it counts as nothing?
well, you don't write plus infinity because that's not really a number. What we're saying here is it's plus any number where that number can be any real number, because the derivative of that would be 0. And officially, we don't see this until 2 slides from now, right? But when you add or subtract functions, you can do the derivative separately. So I jumped the gun there a little bit by adding the 15. That's why I was hesitant to do it right now, because technically we didn't know we could do the derivative of each thing separately. Okay. I'll give you, just to get started on this, get used to it, I'll give you 5-10 minutes to work on these, and then we will keep going.